You are about to step into a mystery where science meets the unknown. Dawn breaks over a remote Siberian forest, and the air seems to hold its breath. A shepherd looks up from a campfire as a second sun flares across the sky, brighter than anything he has ever seen. A few minutes later, the world arrives all at once. A flash, a heat like an open furnace, and then a shockwave that hurls him to the ground. Hundreds of kilometers away, telegraph needles quiver and glass shatters. That morning in 1908, something detonated high above the Tunguska River basin, with a force rivaling a thermonuclear blast, and flattened millions of trees in an instant. No crater, no obvious fragments. Only a swath of devastation and a century of questions. What happened in the skies over Tunguska, and why did it leave behind a riddle that still refuses to close? And if you'd like to help me bring more of these mysteries to life, don't forget to like, comment, and subscribe. Tonight we follow the evidence as it zigzags through witness accounts, expeditions, physics, and rumor. And we ask what this event tells us about our planet's past and its future. The Tunguska event occurred on the morning of June 30th, 1908, in a sparsely populated region of central Siberia near the Podkamenaya, stony, Tunguska River. The blast energy has been estimated in the megaton range, far beyond any chemical explosion and rivaling the largest human-made nuclear devices, which did not exist at the time. In nearby trading posts, people were knocked from their feet. In the village of Vanavara, windows shattered and the ground shook. For nights afterward, observers in Europe reported unusually bright skies, enough to read a newspaper at midnight. But the area was remote, and Russia soon entered years of upheaval. Nearly 2 decades passed before anyone from the scientific community laid eyes on the ground zero of the mystery. That chance fell to Leonid Kulik, a mineralogist at the Russian Academy of Sciences, who became the event's first great detective. Beginning in the 1920s, Kulik led arduous expeditions through swamps and swarms of mosquitoes, guided by local Evenki hunters. When his team finally reached the devastated area in 1927, they found something almost ritualistic. Trees blown down and scorched, radiating outward in a vast butterfly-shaped pattern covering more than 2,000 square kilometers. Their trunks snapped and laid flat like a giant's wheat field after a storm. Yet directly beneath the supposed explosion center, some trunks stood upright, stripped of branches like telegraph poles. It looked exactly like what an intense pressure wave from above would do. But there was no crater, no large meteorite, no obvious metallic debris. Kulik expected a hole. Instead, he found a pattern. From those patterns, scientists began to reconstruct the physics. The best explanation for a radial blowdown with upright trunks at the center is an airburst. An object entering the atmosphere at high speed disintegrates under tremendous pressure and heat, releasing its kinetic energy in the air rather than gouging a crater in the ground. Imagine a small asteroid or comet tens of meters across plunging into the atmosphere at tens of kilometers per second. As the air in front of it can't move out of the way fast enough, pressure builds, the object compresses, fractures, and then explodes in a fireball, converting speed into a titanic blast. The shock wave races outward, flattening trees and igniting fires. The hot plume injects dust and water vapor into the upper atmosphere, brightening the night sky thousands of kilometers away. It is a frighteningly efficient process, and one that hadn't been directly witnessed in modern times, until a much smaller version occurred over Chelyabinsk, Russia, in 2013. That later event provides a valuable yardstick. The Chelyabinsk meteor, about 20 meters across, released energy equivalent to hundreds of kilotons of TNT when it exploded around 30 kilometers up. It shattered windows in 6 cities and sent a shockwave propagating around the globe. A Tunguska-sized body would be several times larger and would penetrate deeper before breaking apart, concentrating its energy more fiercely and closer to the ground. Simulations and blast models suggest Tunguska detonated at a height of perhaps 5 to 10 kilometers, with a yield between roughly 5 and 15 megatons, though estimates vary. Even at the low end, it's a once-in-centuries event. The match between airburst physics and the treefall direction's scorch marks and the absence of a crater is compelling. But compelling is not the same as closed, and Tunguska's file has never quite snapped shut. Part of the difficulty is that the event sits at the intersection of several uncertainties. First, what exactly was the impactor? A stony asteroid, an icy comet fragment, or something in between? Each option leaves different fingerprints. Stony asteroids are dense and tough. They tend to carry iron, nickel, and silicate minerals and can make it closer to the ground before disruption. Cometary bodies are fluffier, ice-rich, and lower density. They can shred higher, leaving fewer robust fragments. Second, how big was it, and how fast was it moving? Small changes in size, speed, and entry angle can produce large changes in the altitude and intensity of the airburst. Third, what should we expect to find on the ground after such an event? Microscopically and chemically. The region's remoteness and the long delay before systematic sampling mean that smoking guns might have weathered away or been masked by later processes. Kulik and later expeditions sifted the soil, dredged peat bogs, and examined tree resins for extraterrestrial residues. Some studies reported tiny glassy spherules, silicate droplets, and magnetite grains enriched with elements often found in meteorites. Others found only ambiguous traces, consistent with the planet's own background. Tree rings from the decades after 1908 showed unusual growth patterns in some samples, possibly responding to changes in sunlight or climate. And there were reports of isotopic anomalies that hinted at a pulse of extraterrestrial material or high-altitude chemistry following the blast. None of it amounted to a trophy meteorite on a museum pedestal. But together these clues supported the airburst narrative. Something from space arrived and vaporized most of itself before it could plant a flag in the ground. One candidate that drew attention in the 2000s is Lake Checo, a small bowl-shaped lake a few kilometers from the supposed epicenter. Some researchers propose that it might be a secondary crater formed by a surviving fragment from the airburst. The idea is seductive. The lake is roughly circular, deeper than neighboring basins, and lines up, depending on the reconstruction, with the trajectory inferred from treefall patterns. However, follow-up surveys painted a muddier picture. Sediment cores and bathymetry suggested the lake could be older than 1908, perhaps centuries old. The geologic setting allows for other explanations, like thermokarst processes related to permafrost. The debate hasn't fully settled, but most impact specialists remain skeptical that Lake Checo is the missing crater. If anything, its controversy underscores how starved the region is of clear anchors. The object's identity, asteroid or comet, matters beyond taxonomy. A cometary fragment would nicely explain the lack of meteorite debris in the bright noctilucent clouds seen across Europe after the event, as water vapor lofted to the upper atmosphere can seed such clouds. An asteroid, on the other hand, better matches the low airburst altitude and the pattern of treefall damage, since denser bodies carry momentum deeper. Some modeling studies split the difference. A fragile rubble pile asteroid, loosely bound rock and dust, entering at a shallow angle could behave comet-like in terms of fragmentation, but still deliver energy low enough to flatten the forest. The best current estimates point to an object roughly 50 to 80 meters across, but best here means a convergence of models and circumstantial evidence, not a fingerprint in hand. Tunguska also sits in a strange liminal zone of human history. It occurred before worldwide instrument networks became common, but late enough that its story spread quickly by rumor and newspaper. Meteorological stations recorded atmospheric pressure waves that circled the globe. Seismic instruments twitched. The aurora-like night glow was noted from London to Stockholm, and photographs from that week show unusually luminous skies. Yet nearly all eyewitness testimonies near the impact were gathered years later, filtered through memory and local legend. Some accounts describe multiple bangs, a fiery trail, a cylinder in the sky, or a pillar of bluish light. As with any extraordinary event, the vividness of the experience can blend with the suggestibility of retellings, leaving historians to triangulate between agreement and embellishment. Where mainstream explanations leave gaps, speculative ideas rush in. Over the years, Tunguska has been credited to an exploding alien spacecraft, a mini black hole tearing through the Earth, a clump of antimatter annihilating with normal matter, or even a misdirected energy experiment by Nikola Tesla. These proposals are colorful, but they struggle against basic checks. A black hole would leave a different seismic signature on exit. Antimatter annihilation would produce telltale high-energy gamma rays and unstable isotopes in distinctive ratios. A technological device would need an origin story and repeatability. None of those tracks have been found. The simplest explanation that fits the widest range of evidence is still a cosmic interloper meeting air at hypersonic speed. That does not make Tunguska dull. It makes it a Rosetta Stone for understanding one of the most consequential natural hazards we face. And that is perhaps the most sobering part of the tale. Tunguska was a planetary defense wake-up call that arrived before our species even knew the term. Objects the size of the Tunguska impactor are numerous on near-Earth orbits. And while our atmosphere can shred them, the energy they deposit can rival nuclear weapons. If the 1908 airburst had occurred a few hours later over St. Petersburg or London, the human toll would have been catastrophic. The Chelyabinsk event in 2013 injured over 1,000 people, primarily with flying glass. Imagine Tunguska's shockwave rolling across a modern city. The probability of another Tunguska-scale airburst in a given century is small but not negligible. Estimates range from once every few centuries to once every 1,000 years. The risk is dominated by the many objects we haven't yet cataloged. That is why surveys like NASA's ongoing near-Earth object programs and upcoming telescopes designed to scan the entire sky every few nights matter so much. Early detection changes a disaster into a plan. With enough warning, even a modest nudge, a kinetic impactor or gravity tractor, can alter an asteroid's path years in advance. In recent years, practice missions have proved that we can hit small asteroids and measure the change. Tunguska's lesson, then, is not only forensic but practical. Study the signatures of airbursts, understand the thresholds at which bodies fragment, and invest in the systems that turn a surprise into a solvable problem. Yet beyond the spreadsheets and simulations, Tunguska holds a more universal fascination. It is a story about the fragility of our assumptions and the patience of the world. For centuries, myths told of fire from the sky. In 1908, a modern world glimpsed the real thing and struggled to make sense of it. The event forced scientists to think about how matter behaves under pressures and heats far beyond the laboratory. And it revealed that Earth's atmosphere is both a shield and a stage, able to absorb staggering energies but also to translate them into shock, wind, and light. It also reminded us that the Earth is not a closed system. We live in a moving target range, orbiting the sun through a field of debris left from the formation of our planetary neighborhood. Most of the time, those pebbles and boulders pass silently. Sometimes they write themselves into our forests. There is also something hauntingly beautiful in the way the evidence connects. The butterfly pattern of felled trees, the standing trunks near the center, the bright nocturnal skies across Europe, the tiny spherules in peat, the global pressure waves. All these are footprints of a single moment. In another sense, the moment isn't done. Trees grew back, the Evenki people continued to hunt. The shockwave rippled into scientific journals and then into planetary defense agencies and then into films and novels. Tunguska became a node where culture, science, and hazard braided together. It is, in that way, less a closed case than a continuing influence. If we try to assign a verdict, we might say this: an extraterrestrial object, probably a small asteroid or a fragile mixture of rock and ice, entered Earth's atmosphere at hypersonic speed, broke apart, and exploded in an airburst at low altitude. The blast flattened over 2,000 square kilometers of forest and lit the night sky across a continent. It left no crater because most of its mass vaporized and dispersed as dust and droplets. It left few fragments because the chemistry and violence of the breakup destroyed them. It left questions because remoteness and time conspired against easy answers. And it left a warning because it will happen again. Stand with me, then, in that Siberian dawn for a last look. Imagine the silence before the wave, the surge of light, the trees bending as if in a single bow. Consider the luck that this happened where it did, and the responsibility that luck implies. The Tunguska mystery is not just about what exploded. It is about what it revealed. A world vulnerable and resilient. A species capable of learning from a shock. And a sky that is both beautiful and blunt. So here's the question I'll leave with you. One that belongs to scientists, policymakers, and all of us who share this planet. If another Tunguska flashed across tomorrow's sky, would we be ready? And what would ready truly mean?